much. Thank you for organizing this really wonderful workshop. So actually, it's first time to attend this QC limit gravity series, but it's really wonderful. Yes, I'm Katsuki Aoki from YITP Kyoto University. Uh, yes, I'll talk about this scattering amplitude and the black hole mergers based on this paper in collaboration with Andrea and Eugene. I'm not so sure that I need to talk about the introduction in this conference, but let me start with some broad things. Probably depending on person or problem, there are a lot of motivation why you are interested in the scattering amplitude. But probably one is just, we just want to understand physics in much simpler way or more fundamental way. So indeed, because we have many possible tools to discuss the physics, like the classical standard equation motion, action, path integral, Hamiltonian, and so on. But sometimes we encounter kind of unnecessary complications. Because for example, you can use, say, action, Lagrangian, but you can put some auxiliary variable and do some transformation, and you can get apparently different Lagrangian. But the two are of course the same. So the physics must be the same. But due to these apparent differences, sometimes we have some kind of confusion. And the same, we have some gauge freedom. And if you choose different gauge choices, apparently we get a different result. But of course, the physics are the same. If we are smart enough, of course, we can deal with all these complications. But if it's possible, it's probably better to through them away and think about a more simpler language. And probably the amplitude is around the appealing candidate of this. And the amplitude means that we just want to use it's just building blocks are just asymptotic on-shell state and their time evolutions, so namely the scattering S matrix. So this is our building block. And in my understanding, this is still on the way, but still it's very difficult to apply this cosmological background. But still, at least in flat space-time, we have a great success. For example, at the practical calculation level, we can actually bypass several unnecessary steps of the computations. So it's like so we can use, say, unitarity, and then this actually simplifies the calculation a lot. So this is one good thing. Or even at the conceptual level, we have a very good advantage because we can get the universal view of the apparently different physics. As I said, sometimes the Lagrangian are different, but they are the same. Or we can bring this idea, brings the idea of the EFT or double copy. And in fact, this leads to the new idea of this gravitational wave and scattering amplitude. And this is probably one of the hot topics in this conference, and my talk is along this way. And so actually, I joined this field relatively recently, but usually the people think about the scattering problem of the black holes. But it's probably natural to think about, or at least try to apply these ideas to the problem of the black hole merger. So there are obvious motivations because at least one obvious one is comes from the observations because our main target of the current gravitational waves are just the gravitational waves caused by black hole mergers. So that we now have a lot of the signals, so probably we need more understanding of the black hole merger. This is one motivation. Well, even apart from any observational experimental things, it's probably already interesting to think about the black hole formation in the scattering amplitude. Because even at the classical GR level, the formation of the black hole merger of the black hole sounds very, very complicated process. So it sounds like the structure of the space-time is completely different from the past and the future. So it's really a complicated process. And maybe it's more challenging to understand this process in a quantum sense. So it's probably not interesting if you can get any hint to think about this process by using scattering amplitude. So actually, maybe broadly speaking, my motivation here is just a very simple question. So what is black hole? So this is a question, and let's try to answer it by ourselves. So let's think that how we see the black hole in this on-shell perspective. The point is that, as I explained, the basic ingredient in this on-shell approach is just a asymptotic state. So there is no notion of the local observer. The observer are always at the infinity. So we should think that how a distant observer will see a black hole. In that case, a black hole is indeed a very simple object. So it's just a localized object with mass and spin. So it's almost like a one-particle state. It's just standard one-particle states described by mass and spin. But of course, the people say that the black hole has a structure. It has a horizon or external gravitational field. But the point is that, as I said, the observer is just at the infinity. So there is no local observer. So observer doesn't directly see the horizon. They always see the horizon effect as just a response to the external force. So this is nothing but the standard scattering experiment. So that all the features, local features, must be explained by the existence or probably absence of certain interactions. For example, there are great papers about the black hole has a minimal coupling to gravity, so this explains the gravitational force. And also there is no lab number of the black hole, meaning that there is no certain interactions responsible for lab numbers. So they all suggest that the black hole seems to be indeed a particle with just the interaction. So black hole may be just a particle. So let's accept this on-shell view. Then the merger of the black hole sounds really a simple process. It's just a standard fusion process of the particles that we are really familiar with in the quantum physics. So this is our whole idea of this talk. So the maybe black hole is just particle in the on-shell picture. Then the merger of the black hole that sounds very complicated, but of change of the space-time. But it may be just a fusion process of the particle. So the rest of the time, I will try to explain how to practically think this picture and how to compute several observables. So let's go to the amplitude. So as I said, we immediately encounter the first difficulties. Black hole is very non-perturbative. So people say that it's non-perturbative, so there is no good analytic control to describe this merger. That's true. This is completely non-perturbative physics. But we actually have a nice example in the QCD. So it's QCD means gravity. So we have the physics of pion hadrons are completely non-perturbative physics from the viewpoint of the original QCD. But on the other hand, we can always prepare the effective field theory, so chiral EFT. So now the pion is now the fundamental, in a sense, fundamental degrees freedom in the EFT, and we can build the theory for this pion directly, not using the QCD. So the merger may be the same. So sorry. So merger is non-perturbative, but in any case, this is just a local reaction. So this means that this should be described by just local effective operator, just 3-point perfect, 3-point amplitude. So let's now think at the merger process from the two Schwarzschild black holes into the Kerr black hole. And Schwarzschild means that they must be a just spin zero state, and Kerr must be a spinning state. So let's first think that the Kerr is a just spin L state. So this is just 3 points, so massive 3 point, and we have a complete fluctuation of all the possible 3-point amplitude. So we know the answer. So we don't need to refer to the original GR problem. We just use this 3 point. So this is the massive spinor helicity variable, and maybe all of you are familiar with it. But if you fix the center mass frame, this is nothing but the spherical harmonics. So anyway, this 3-point is completely fixed by kinematics. And of course, we have unknown information. So this is a coupling constant. So basically, the Lorentz invariance fixed this form, but we have an unknown coupling constant, and this coupling constant has all the information of this merger process. But it's just 3-point process. So the actual question for us is now that how to determine this coupling. And again, the good point is that the black hole is very simple object. So the coupling should be determined to recover the future of the black hole. And you know the future of the black hole is the existence of horizon, and the future of the horizon is that nothing can escape the horizon. And this is a statement in the classical GR, but we are now talking about the scattering amplitude. So we should translate this GR statement into the statement of the scattering amplitude, and this is nothing but the complete absorption process. So let's explain it a bit. So let's consider just elastic scattering, not the absorption process. It's just a standard elastic 2-2 scattering of the two black holes. And this is just standard 2-2, so that we can use a standard partial wave expansion. It's just text vector. And we can write this partial wave, the amplitude in this form. So E is center mass energy, P is momentum, and eta is important. So eta is called elasticity parameter, and this takes the value between 0 and 1 by the unitarity. And 1 corresponds to the elastic process, so there is no absorption in this elastic process. And 0 corresponds to the partial complete absorption. So that means the corresponding S matrix, partial S matrix, is 0 for this eta equals to 0. So this is just the elastic process. But now let's think about the classical black hole problem. So in the classical, so of course the dynamics is complicated, but let's just think about the kind of the intuitive picture. So if in the classical, we know that if the angular momentum of this system is small enough, basically smaller than typically this value, then just the two black holes collide and form a new black hole state. And this is the classical physics. But the point is that we know that the black hole never decay into the two black hole state, at least in classical sense. So that means that if the angular momentum is smaller than this critical value, this two initial system never come back to the original two-body system. So this means that the corresponding S matrix must be 0. And this is nothing but the eta equals to 0 for complete absorption. So in this way, we can know how to fix this coupling constant. So the point is that actually we can compute the absorption cross-section from this process, because the total cross-section is just the imaginary part of this elastic amplitude, and the elastic cross-section is, of course, computed by just square of this elastic amplitude, and difference is absorption. And this is very simple process, so we can easily compute this absorption cross-section. On the other hand, we are now interpreting that this absorption cross-section comes from the intermediate black hole, the formation of the black hole. So, and we know that this 3 points, so the square is easily computed, and we get the one matching condition to the coupling, or precisely speaking, coupling square times spectral density is completely fixed to recover this complete absorption process. So in this way, we can fix the 3 point. But we should also mention that the relation between the kind of quantum black hole formation and classical black hole formation. So the difference is that the treatment of spin. So I say that the formed state is something like a spinning state, spin L state, but it's something like a quantum state because the spin is traveled by discrete numbers. On the other hand, we are expecting the classical black hole formation, meaning that the spin must be a continuous number. And there is a great paper with Rafa and Alex. So that they use a so-called coherent spin state. So as the name says, that this is just a coherent state of the spin. And this is nothing but the superposition of the all spinning state with certain weight. So in this way. But anyways, this is some the change of the basis to the discrete state to the continuous state. And the good point of this coherent spin state is that now the spin of the final state is defined by the expectation value of the spin operator. And this is given by basically alpha squared. So tilde is the conjugate and sigma is part matrix. But anyway, that's given by just alpha squared. And alpha is just weight. So that this is continuous number. So that this state has the continuous spin. And we can interpret this as a kind of classical black hole state. And the transformation from this discrete spin state to the classical continuous state is straightforward because this is just sum. So we need to just sum up all the spin amplitude. And actually, the result is very simple. It's just exponential. So this is the 3-point amplitude from the two Schwarz sheet into the black hole. And this is the basic building block. So this we can use this 3-point to compute a more higher point amplitude, and we can compute the observables. And probably I don't need to explain this, but anyway, just in case, let's briefly explain how to extract the classical physics from the scattering amplitude. So I use this KMOC formalism. So this relies on the very kind of elementary thing of the quantum physics. That's why this can be applicable to essentially any situation. So the point is that first of all, the observable in the quantum physics are expectation value. And we are interested in classical physics, so we are interested in the dynamics of the system. So we are interested in the change of the observable. So the change of the observable is nothing but just the expectation value at the out state minus the in state. And the out state here is related by the in state via time evolution. So that this is just S times initial state. So it's very simple. And also of course, we should carefully choose the initial state to recover classical physics, because usually in the scattering amplitude, we use the plane wave state. But plane wave means that the state is explained in the whole space-time. But the classical physics means that the object is localized. So we should use instead the wave packet state. Wave packet state. And this should recover the classical localized object in this h bar goes to 0 limit. So we need to multiply certain the wave functions and shift it by the impact parameters. But anyway, in this case, this is just some certain integral of the plane wave state. So if you substitute this into that one, then essentially the observable is just some integral of the standard scattering amplitude represented by plane wave. And then we finally just take h bar goes to 0, then we can recover classical physics. So it's very simple. So that we can recover classical physics by just using on-shell scattering amplitude and state. So there is no need of the classical EOM or classical physics. Let's use it. So first, let's consider the simplest merger process. The simplest means that there is no radiation. So it's just a kind of conservative merger process. So in this case, the whole process must be described by just 3 points. And the important point here is that now this is exponentiated. And also this alpha, so basically the eigenvalue of this coherent spin state, should scale as h bar minus half. And if we take a classical limit, this alpha goes to infinity. That means that this is the modular square. So this means that the exponent is very large negative value in general. So this means that in general, if we take a classical limit, 3-point vanishes. So there is no process. And this is there is an exceptional case. So this 3-point is non-zero only if this kinematic part is cancelled by this overall normalization part. And this gives a conservation rule. So we find that actually if we take this classical limit, this 3-point just goes into the delta function. But more precisely speaking, this is a 3-point for the plane wave state. So we should move to the kind of momentum space by taking a Fourier transform. And this is indeed what we need to compute the observable. So that this is nothing but a Fourier transform of the 3-point. And this goes to the 4 delta functions. So here I use a center mass prime, so it looks a bit complicated. But the role of this 4 delta function is very simple. So these gives a 4 constraint for the 4 components of the spin vector. So all the components of the spin vector is now completely fixed by the initial orbital angular momentum. So in this way, we can recover classical momentum conservation and the angular momentum conservation loss. So we can compute the observable by using KMOC, and the momentum conservation is almost trivial. This just comes from the factorization of the S element to the delta function and amplitude. So this is really very easy to understand. On the other hand, the spin conservation is a bit non-trivial, but we found that the 3-point indeed plays a role. So the 3-point gives the delta function, and this finally gives the angular momentum conservation role in the taking a classical limit. So in this way, we can see that the classical conservation indeed comes from the macroscopic conservation and the role property of the 3-point. But it's kind of trivial thing in the classical physics. So let's go to a more non-trivial thing, the emission of the gravitational waves. So the waveform in the KMOC is, again, just the expectation value. It's just the expectation value of the gravitational operator. And we can insert the completeness, because this is now squared. And then we can get this form. So roughly speaking, the waveform in the frequency space is given by the certain integral of the 3-point times 4-point. And this 3-point is this merger 3-point. And 4-point means that initially we have a 2 black hole state, and the black hole formation state, and 1 gravitational emission. So the different from the standard elastic case, this is always a squared form, because usually this linear piece comes from the 1 of the S. So S is divided to 1 plus IT, and 1 survives in the elastic process. But now we are considering merger process. It's not the elastic process. That's why this always comes from the squared form, or cutted form. But anyway, this is what we want to compute. So we want to just compute some integral of the 3-point. We already know it. And what we need is just computation of this 4-point. But we now have the building blocks. So we have the 3-point functional amplitude for the merger. And we also know that how the black hole couples to the graviton. And in general, we need a probability loop amplitude. But anyway, this is just first step. So let's just consider the simplest one. So this is just a 3-level process. And let's just compute the 3-level amplitude and 3-level waveform. And actually, 3-level 4-point is very simple form. So this is the result. So I didn't write any definitions. It doesn't make sense. But anyway, the point is that it's just given by the factorized form. So the 4-point, this is the 4-point from the 2 initial 2 black holes and 1 final black hole Carl state and 1 gravitational emission is given by just the 3-point times certain soft factor. And we have some compact expression of this soft factor, but it was interesting that this factorization doesn't require any soft limit, essentially thanks to the use of the coherent spin state. But anyway, we get this simple expression of the 4-point, and just substitute this 4-point into our formula of the waveform, and just do the integral. And the integral is very simple because essentially it's just fixed by the delta function, momentum conservations. And finally, we see that the spectral waveform is nothing but the soft factor. And the kinematics is now fixed by all the delta function constraint. The result is probably not so surprising because you already probably know that the relation between the memory and soft theorem. And indeed, this waveform is, of course, the kind of spin memory effect. But at least we have 2 updates in this context. So one is that, as far as I know, this spin extension of the memory was known only up to the linear order in spin in the purely classical calculation. Well, there was a kind of conjectured result up to the quadratic order in spin. But our result is actually all order in spin. So this essentially comes from this nice result of the minimal coupling of the graviton. But anyway, we actually have the spin memory effect at all order in spin. So actually, we get a new result by using this functional technique. And this is one thing. And another thing is that in the standard story, usually people first compute the soft theorem in the quantum side and compute the memory effect in the completely classical side, and they just compare. And this can answer the two are the same, but this doesn't answer why they have to be the same. It's maybe just a coincidence. But our result is purely on shell. So we just compute the on shell amplitude and just define the observable and just do the subcomputation and then show that the waveform is indeed given by this soft factor. So in that sense, our result can be regarded as an on-shell proof of the memory equals to soft theorem at all spin orders. So this is the one result. But this is kind of just a memory type. So it's theoretically interesting, I think, but at least in the astrophysical sense, it's not very interesting because this is super low frequency part of the spectrum. And people are typically interested in the relatively large frequency side of the spectrum. And but the point is that our previous result is just based on the tree level, and we have to add more loop diagrams because the tree means that essentially there is no gravitational exchange, so there is no dynamics basically. But if you want to add the gravitational force between two black holes, probably we need a loop effect. And they may give some realistic waveform, and probably I think that we need a certain resummation if you really want to reproduce a major waveform. But and if this resummation is kind of agonal type, maybe there is a way to deal with it. But anyway, this is kind of difficult problem, so let's deal with formwork. And let's first consider simpler setup. So before going to that. So the simpler setup is just taking a large mass ratio. So that's always the case. So we assume that the second black hole is much lighter than the first black hole. Then this heavier black hole is treated as just a classical background. Then the problem is reduced to the potential scattering problem. It's basically the same as how we can reproduce the quantum mechanical scattering problem from the QFT scattering problem. Or in this context, it's sometimes called the zero self-force approximation. But actually, this is good because this also gives a clear comparison between our on-shell approach to the standard black hole quantum theory. So rest a few minutes, I will talk about this. So now let's just consider standard classical or standard GR scattering problem. And so the one black hole, well, generally speaking, we can think this background spacetime as an effective one-body picture, so that we can think this is a motion for the center of mass motion. But anyway, let's suppose that the first black hole is heavier than the second one, and the first is treated as a classical background, just a Schwarzschild. And on the other hand, we just only solve the dynamics of the second black hole, and now I keep the kind of quantumness, so that I just solve the Klein-Gordon. But anyways, if we take a classical limit, then this reduces to the geodesic and reduces to the classical two-body system. But this is really a well-known scattering problem in GL. But the point is that now we are considering a black hole spacetime. So that means that we have two different boundaries. So the standard infinities, the time-like infinity to infinities, and also the horizon boundaries. And due to the existence of two different boundaries, we now have four different mode functions as a solution of this Klein-Gordon. And the first two are the standard in mode and out mode. They are also called in mode and out mode. And indeed, they are regarded as the in state of the out state of this scattering problem. So because this in mode, for example, is a particle emitted from the past infinity, past time-like infinity. So this is just one particle state in the past infinity. But here the point is that we also have a background. So this is just a wave for this Klein-Gordon, but we also have a background. So that means that if we back to the kind of QFT picture, we should understand that this state, this wave function, as a two-particle wave function. So composed of black hole 1 and black hole 2. So background plus this particle on the past infinity. And this is the same. So this is now the outer state, so future state. And it's composed of black hole background and the particle. But we also have two more mode functions. They are often called the up mode and down mode. And this is a bit physical state because this is a particle emitted from the, say, white hole horizon or go to the black hole horizon. So they are something like a particle living on the horizon. But the point is that we should use our on-shell picture so that we should understand that this mode function at this point of view. So how the distant observer sees them. And in that sense, we can give a clear answer. So the point is that let's take this down mode. And in that case, the observer is at the future time like infinity, because in the past, it's not the ideal state, so we should think about the future. And in that case, the particle is just on the horizon. But observer is at the infinity. So that means that the observer actually doesn't see any wave at his point. And so the observer cannot distinguish whether this comes from the state, comes from the background plus perturbation, or just one particle state. Actually, the observer must see that this state as a composite one particle state. And this composite means that now that this is composite of the black hole 1 and 2, so that they don't separately see the two states. They are always composite. So that this is now the one particle state rather than the two particle state. So that we now give this interpretation. So that this up mode is the one particle in state, and this is a composite of the 1 and 2, and this down mode is a composite of the 1 and 2 for the out state. And having these interpretations and using standard inner product of the quantum mechanics, we can just compute the S matrix element. And this is a standard into the out transition, and this is the standard elastic scattering amplitude. And we also have a new part, and this is a transition from the in state to the down mode, and this is a two particle state to the one particle state, so the merger waveform and merger amplitude. And indeed, this 3 point exactly matches our 3 point, on-shell 3 point. In this way, we can connect our on-shell picture to the standard classical GR, not classical, but anyway, GR picture. And we can also go more. So we can also compute the emission 4 point. So now we want to compare this black hole 2 state into the black hole X state, so the formation state, and one graviton emission or radiation emission state. But as I said, that this two particle state is described by this in-mode function, and this formed state should be described by down state. And we have a one more emission, but this emission reaches to the infinity. This means that this must be described by out state. So that this is transition from the in state to the down plus times out state. And here I just use a so-called Patavina approach to postulate that the amplitude is given by the on-shell action. But anyways, we can compute this transition probability, and this is the answer by just the integral of some model functions. And here, for simplicity, I don't consider the graviton emission. I just consider the scalar wave emission, but the essence is the same. It's just we have some indices, but it's just the inner product, or it's just integral. And now we have this 4 point amplitude, and this is in a sense non-perturbative in G, because we don't need the expansion in G if we know the full form of these wave functions. And then we can use this 4 point and use a KMOG to compute the waveform. And the good point here is that, of course, this is well-known classical GR problem. So we can also use a classical equation motion and solve the emitted waveform by just solving the standard Einstein equation and Klein-Gordon equation. And we can just compare. And actually, we see that the exact agreement of them, so maybe of course. So that point is that using this 4 point indeed reproduces the classical waveform in this extreme mass ratio limit. So that gives a kind of proof of concept. So the black hole merger, actually it's from the inspiral to Lignan, all the process can be in principle computed by scattering amplitude. And this is the main message of this talk. So this is a summary slide, but maybe, and also some discussion, but maybe I can finish it. Thank you very much.
Hi. Sorry, I have a basic confusion. So we normally justify the point particle approximation by some separation of scales. We say the Schwarzschild radius is much smaller than the separation between the black holes. But that's clearly not true in this merger process.
I think we are going more.
But
so we are really interpreting black hole as a particle in the S matrix sense.
Right, but what's the small parameter that you're using to control this effective description?
That's probably more technical question. How to compute this 4-point process or more higher point process. And our expectation is that this loop expansion may be the omega expansion, because the tree level gives a memory waveform, and memory should be valid only for very small frequencies. And to be honest, we didn't compare the loop correction, so that we are not sure. So we cannot answer your questions what the expansion parameter is. But our expectation is that the loop expansion may be omega expansion, G omega expansion. And of course, we have a missing mass dimensions. We are not sure. But G omega something expansion. This is our expectation. So that if you are interested in just low frequency regime, then maybe we can use this expansion technique. But if you are interested in high frequency regime, then probably we need a certain resummation, probably Aoki type resummation. That's our expectation, but it's just the beginning of this program. So we still don't know. It comes from the just conservation. So at least in the case of the no emission, we can define the mass of the final state as just the p square, right? And p is just yes, p is just defined by the expectation value. And if you compare square of it, it gives a mass.
But the mass is smaller than
Yes, so
twice the mass.
This is the non-radiative case. That's why we get the Pf equals to P1 plus P2. But if we add the radiation, we can easily see that the final mass is given by the initial total energy minus radiated energy.
So the mass is fixed by experiment and also the coupling G, right?
Coupling G doesn't end basically. Basically, the conservation just fixes it.
Yeah, but in the process, the scattering process depends on the
So in that sense, we have to compute the radiated energy. And this is something like a square of the 4-point or higher point. And if we can compute it, we can compute the radiated energy by a gravitational wave. And then we can compute the mass.
But when you say compute from scattering amplitude to
we
the
can
whole
compute it by
process,
scattering
you need to
amplitude.
fix GF and you need to fix the max of the black hole after the merger, and you have to do it for all possible masses, right? So it's
okay.
How do you predict something?
Okay. The good thing is that always observable is in. Observable is always in. So we should insert the completeness relation here. That's why all the possible mass appear during the intermediate computation. But the good thing is the classical limit. We often have the delta functions. That's why this delta function pick up the specific state. Then this enters the final calculation.
Okay, Julio.
Yeah, maybe it's related, but there was this coupling G in that 3-point amplitude that you said that you have a matching condition in
Yes.
terms of the absorption cross section.
Yes.
How are you going to compute that? I mean, you need to do a matching calculation to GR to this process of like two black holes merging. That sounds like something very hard to do in principle. So is there any hope to determine this coefficient from an actual matching calculation? Or is it just trying to understand the kinematic structure of the result, but we don't think we're going to be able to measure this coefficient?
So probably if we really want to intersect the equal mass mergers, probably we need to match it with mechanical relativity. This is very hard. But at least in the case of Emily, so this is what we did here. So I didn't write any explicit expression, but we can compute the process. Basically, it's given by some transmission coefficient times some kinematic thing. And if we take a classical limit, transmission becomes just 1. Then this gives a complete absorption. But if we keep the correction, kind of quantum correction, then the transmission is not 1, and this affects the final G. But anyways, roughly speaking, this G in this Emily is just transmission. And transmission is 1 in the classical limit.
Okay, we have one last question.
Thanks for an interesting talk. Also, this is related to the 3-point. So here, the kinematics is determined by the masses of the black holes, and I'd assume that this approximation is neglecting the fact that we have radiated energy, and this is not negligibly small. So, but one thing that we can argue here is that when the mass ratio is extremal, or if the mass ratio is large, then the radiated energy is small, so that we can try to argue that this is a good approximation. And that leads to this question. Do you have a good argument or good understanding of whether the mass ratio expansion is going to be a convergent series or an approximation that makes sense in this approach?
That I don't know if the mass expansion is convergent or not. That I don't know.
All right, so we end here. Let's thank Katsuki again for that